In the previous video, we started talking about secular terms as a motivation to studying a new kind of perturbative method, which is the multi-scale method of multiple scales. Um, so there we considered a linear second-order differential equation subject to forcing, which led to a resonant interaction between the forcing and the natural frequencies of the system, and that gave rise to a secular term. But now let's consider an equation where the secular term arises as a result of a resonant interaction between terms of consecutive orders in a perturbation expansion, which is our sort of main idea behind using the multi-scale methods subsequently. So for that purpose, let's consider an equation known as the Duffing equation, and this is named after a German engineer, George Duffing, who was essentially studying a somewhat generalization of this particular equation. So the equation that we're looking at is an equation of the form d2y dt square plus y plus epsilon, where epsilon is a small parameter which we'll assume to be positive, much less than 1 and greater than 0. So plus epsilon y cube equals 0. So this is now a second order nonlinear differential equation where this is actually a term which is nonlinear in y. So this is a nonlinear term. And again, we're assuming that this equation is given to us in some suitably non-dimensionalized form, where y is our dependent parameter and t, our independent parameter, is time. And we take this equation subject to the initial conditions that y at time t equals 0 is 1, and the first derivative of y at t equals 0 is 0. Now, just as a physical motivation where this kind of an equation could arise, it's, for instance, if you consider the motion of a pendulum, and we do not, so typically the force that the pendulum experiences as you displace it from its equilibrium position is a nonlinear function sine of theta, depending on the angle. It's only when we linearize that equation to linear order, like we do a Taylor expansion of sine theta, that we get a linear second order differential equation which looks like this. However, if you retain higher order terms, then you might pick up a term which is actually a cubic term in theta. And the equation that Duffing actually studied also has a damping term. So for instance, you might have a term like dy dt, which is sort of like which damps the motion of the pendulum. But again, like we'll not worry too much about what physical model that this equation is representing for now, and focus simply on how to use this, how sort of this equation, when we want to study it perturbatively, gives rise to secular terms. And again, so why do we want to study this equation perturbatively? It's again because it's a nonlinear second order differential equation, and typically such equations, it's very hard and it's very rare that you'll find exact analytical solutions to such equations. But if you can identify a small parameter like an epsilon here, then it's possible to get some approximation to the solution by using some perturbation methods. So let's see how we can study this equation perturbatively. And again, just as a reminder, the idea is to look for a solution of y which is of the form y naught plus epsilon terms y1, and we just retain, we just study it perturbatively to first order in epsilon, and so we'll ignore all terms which are order epsilon square and higher. So we'll make this ansatz, put it in this equation, solve for y naught, then solve for y1, and that will give us a first order approximation to the solution of this differential equation. And again, we also know the initial conditions. So y at 0 is 1, and dy dt at t equals 0 is 0. So we'll use that to solve for our the constants that arise in our equations. So let's see what happens when we make this ansatz and put it into this equation. What are the terms that appear in the equation in orders of epsilon? So differentiating this equation twice. So let's look at one term at a time. So let's say this is our first term. This is our rather d2y dt square is our first term. Y is our second term, and this is our third term. And let's see what all terms are relevant in the perturbation expansion for each of these. So d2y dt2 will give rise to, so we just differentiate this equation twice, and we'll have terms like d2y naught dt2 plus epsilon d2y1 dt2. So these are the only two terms that will come out of the first term d2y dt2. The second term is y, and again that will just give us y naught plus epsilon times y1. The third term is epsilon y cube, and here we'll substitute y naught plus epsilon y1, and we have to cube this. Now notice that there is an epsilon prefactor appearing before the cube, and so the only term in the cubic expansion that will have an epsilon to linear order is simply the cube of the term y naught, and so this will be approximated as epsilon y naught cube, and all other terms which appear in the expansion of the form are of the form epsilon cube y1 cube plus 3 y naught epsilon y1, 3 y naught square epsilon y1 plus 3 y naught y1 squared. So again, to order epsilon squared. So all the other terms that will appear are either epsilon squared or higher than that. So the expansion to this would be order simply epsilon y naught cube plus big O epsilon squared. So this is the only term that we pick up from the cubic expansion of this. So let's now put this ansatz into the equation and collect terms of like orders in epsilon. So the first, the epsilon 0 to epsilon 0, the terms that we'll sort of retain are d2y naught dt2 plus, so that's the 0th order term coming from d2y dt square from here. The 0th order term coming from the y term is simply y naught, and there is no 0th order term coming from the epsilon, the nonlinear term, which is epsilon y cube. And so the equation that we left with is simply this. And this equation we know how to solve, and I'll put a link to previous videos if you have solved this equation. So the solution to this equation is y naught is a cosine t plus b sine t. Okay. Now we also know the initial conditions, which is that y at t equals 0 is 1, and the first derivative of y at t equals 0 is 0. So that we can use that to evaluate these constants. So let's just look at what happens to the initial conditions. So y at t equals 0 is of the form y naught at 0 plus epsilon y1 at 0, which we want to be equal to 1. And so the initial conditions that we need is y naught at t equals 0 is 0, and y1 at t equals 0 is 0. So again, what we're doing here is we're comparing the left hand side to the right hand side to evaluate the initial conditions. The right hand side does not have any term containing an epsilon or higher order terms. So all the so we're comparing like powers of epsilon on both sides, just like we've been doing before when we started perturbation theory, when we started talking about perturbation theories. Like we're assuming that we can compare terms appearing in a perturbation expansion in orders of epsilon. We can just compare terms which are of like orders in epsilon, just like we can do a comparison when we're talking about Taylor series expansions. And again, just as a reminder, this is sort of not a very rigorous step. Like it's not easy to justify why we can compare terms of like orders in epsilon, but this is a working assumption we always make. We tend to make when we talk about perturbation expansions. So this gives us the first initial condition for y naught, which is the 0th order expansion term, is that y naught at t equals 0 is, it's 1, and y1 at t equals 0 is 0. And then we differentiate this again at t equals 0, and this will give us, and for derivative we can also use the symbol prime. So this will give us y naught prime at 0 plus epsilon y1 prime at 0 is 0, and so y naught prime 0 is 0, and y1 prime 0 is 0. So these are the initial conditions that we need to use, and just highlight them again, this and this, to evaluate these constants. Okay. So for this particular equation, we know that y0 at 0 is 1. So what's the complete solution, or rather what's the what are the constants a and b? So y naught at 0 is 1, which is a cosine 0 plus b sine 0. So this is already 0 because of the sine 0, and this gives us a equals 1. And the derivative y naught prime at 0 is minus a cosine 0 minus a sine 0 plus b cosine 0, and this should be 0. and this gives us b is 0. So the solution to this equation is simply cosine of t, because a is 1 and b is 0, subject to these initial conditions. Okay, so that gives us the 0th order approximation to this differential equation. Now what about the first order term? The first order equation will be d2y1 dt squared plus, we have the first order term from here, which is y1, plus the only term, if you recall, that we get from epsilon y cube is simply is the term epsilon y naught cube equals 0. And so this is the differential equation for the first order correction to the perturbation expansion of our solution for y. Now this equation can be written in the form d2y1 dt2 plus y1 equals, sorry, no, it's not here, equals minus y naught cube. Okay. Now this is interesting, because this is again this is again a linear second order differential equation y1, just like this is a linear second order differential equation y0. However, there is a forcing term to this equation, which is of the form minus y0 cube. And this is what we mean when we say that there is an interaction between terms of consecutive order in a perturbation expansion. In this case, y0, the solution, the 0th order solution y0 acts as a forcing to the differential equation that y1 satisfies. Now we've already solved for y0, right? So we know exactly the form of the forcing. In other words, the forcing that takes place is d2y1 dt2 plus y1 equals minus cosine cube t. Okay, and now we have to solve this equation subject to the initial conditions that y1 0 is 0 and y1 prime 0 is also 0, which we just worked out. Now let's simplify cosine cube t and write it in a form that we already know how to solve for the forced solution for this differential equation. So again, the solution for this differential equation will have two parts, a homogeneous part and a forced part, or a particular solution. The homogeneous part, which is just this part, so let's just write down homogeneous solution first. So the homogeneous solution to this equation y1, let's say homogeneous with time t, is again of the same form as this. It's of the form some constant, let's just say, let's just write it again as a, or rather a1 cosine t plus b1 sine t. And now we need to work out what's the particular solution to this equation. Okay. Now cosine cube t can be simplified, and one of the ways we can do that is to actually use Euler's identity, which we've been talking about in the series on complex analysis. So let's see how Euler's identity is actually useful to simplify some of these trigonometric functions that arise. So if you recall, cosine cube, or rather the Euler's identity e to the power it is cosine t plus I sine t. So the real part of e to the power it is actually cosine t. Now how do we use this to evaluate something of the form, let's say cosine cube t, in terms of simpler functions which are linear in time, or which are sort of linear in which do not have a cube, which are like something like cosine t or higher frequencies. So one of the ways to do that is to actually cube both sides of this equation. So you raise both sides to the power of 3, and we find that that is cosine t plus I sine t whole cube. But e to the power of 3it satisfies its own Euler's identity, and it can be written as cosine 3t plus I sine 3t. Okay, so if we can cube this and compare its real part to the right hand side, we'll be able to evaluate cosine 3t. And from there, since when we cube this, we see that we'll have a term of the form cosine cube t, and that might give us an expression for cosine cube in terms of, let's say, cosine 3t. So let's see what happens. So let's cube this. Now the cube of this is cosine cube t plus I cube sine 3t plus 3 I cosine t sine t cosine t plus I sine t equals the right hand side. So again, let's collect the real part and the imaginary part from here. So the real part will be cosine 3t. Now I cube is minus of I, so that will be an imaginary term. The real term will come from product of these two, and that's essentially 3I square cosine t sine square t. So I square is minus 1, so this will be minus 3 cosine t sine square t. And if we compare, so this is the real part coming from this entire expression, and this real part should be equal to cosine of 3t. And likewise we can compare the imaginary parts, but let's skip that for now. Now sine of square t is 1 minus cosine square t, so we can simplify this further and write this as minus 3 cosine t 1 minus cosine square t equals cosine 3t. And this gives us cosine cube t minus 3 cosine t plus 3 cosine square t. So this gets added here. 4 cosine square t is cosine 3t. Or in other words, cosine cube t can be written as 1 over 4 cosine 3t plus 3 over 4 cosine t. Okay. So this particular forcing can actually be written as, so this is cosine cube here, cosine cube t can be written as 1 over 4 cosine 3t plus 3 over 4 cosine t. So let's write it in that form. So the forcing this here can be written as or d2y1 dt2 plus y1 equals minus 1 over 4 cosine 3t minus 3 over 4 cosine t. Now how does this help us? Now if you recall the previous video, we have already solved an equation. So there are two forcing terms here, one of the form cosine 3t and another of the form cosine t. And these two forcing act independently of each other, because this is a forcing which is at a frequency which is thrice the frequency at which this is forcing. And these two sort of can be thought of as two independent forcings applied to this differential equation. Now, if you recall our previous video, and I'll put a link there, if you have an equation, a linear second order differential equation of this form, subject to a forcing, let's say some constant a cosine omega t, then the solution, the particular solution to that equation is of the form cosine omega t, or rather a cosine omega t divided by 1 minus omega square. Now if this is when omega is not equal to 1, when omega is equal to 1, the solution is of the form a over 2 t sine t when omega equals 1. So we worked out both these cases. One when so for us omega is 3 is the first forcing term, and the second forcing term is when omega is 1. And notice that this particular forcing is actually this particular forcing, the frequency at which this term is forcing the equation is exactly the natural frequency for this second order linear differential equation. And this is what gives rise to the secular term. And that is why it was important to write cosine cube t in the form of a higher frequency in this particular form, because that shows very clearly that cosine cube t is actually composed of two different kinds of forcing, a cosine 3t and a forcing cosine t, which actually is a forcing which interacts resonantly with the natural frequencies of the system. And so the particular solution for this equation will be y particular. So a for one of them is minus 1 over 4, so it's minus 1 over 4 cosine 3t divided by 1 minus omega is 3. 1 minus 3 square is 9, which is minus 1 minus 9 is, so let me just write down, 1 minus 9 is minus 8. It's minus 8, and therefore the solution is plus 1 divided by 32 cosine 3t. Likewise, the solution coming from this term is of the form, so again the frequency is omega is 1, whereas the constant that's appearing in front of it is minus 3 over 4, so it's minus 3 over 8 t sine t. Okay, so the total solution for this equation, the total particular solution for this equation is of the form 1 over 32 cosine 3t minus 3 over 8 t sine t. And now we can write down the complete solution, which is to this differential equation, which is of the form y1t is a1 cosine t plus b1 sine t plus 1 over 32 cosine 3t minus 3 over 8 t sine t. Okay. And now if we write the total solution, which is y0 plus epsilon y1 to the whole differential equation, and in fact we can also solve for a1 and b1 using the initial conditions. So let's do that actually. So y1 at t equals 0 is 0, and y1 prime at t equals 0 is also 0. So y1 at t equals 0 gives us a1, this term is 0, plus 1 over 32, and this is 0. So that gives us a1 is minus 1 over 32. And the second term is that y1 prime at t equals 0 is also 0. So 0 is, we have to differentiate this, is minus a1 of sine t, which goes away, and then we have b1, and then the derivative of this term, which is minus 3 over 8. So the first, there will be two terms coming from the chain rule. So 3 over 8 t cosine t, which at t equals 0 will go away, and then we have minus 3 over 8, the derivative of t, and then sine of 0, which also goes away, and so b1 is simply 0. So we have a1 is minus 1 over 32 and b1 is 0. Okay, and so the overall solution is this goes away, a1 is minus 1 over 32, so it's minus 1 over 32 cosine t plus 1 over 32 cosine 3t minus 3 over 8 t sine t. And the total solution for y, which is y0 plus y1, is of the form cosine t was y0 plus epsilon times y1t, which is minus 1 over 32 cosine t plus 1 over 32 cosine 3t minus 3 over 8 t sine t plus order epsilon square. Okay, so this is our perturbative expansion to the solution of this Duffing equation to order epsilon square. Now notice what's happening. For times t, which are of 4 times t, if time t is of the order of 1 over epsilon or greater, for large times which are greater than 1 over epsilon, we find that this term actually starts becoming more and more dominant, and then the solution for y is no longer bounded. For times which are smaller, which are much less than order 1 over epsilon, we find that this term is still small, and this is an okay approximation to the solution. But for times which are large, which are much greater than 1 over epsilon, we find that this particular solution that we have derived is no longer a good perturbative solution to the differential equation. Now, why is it that this is a problem? Now, why is it that this solution is not a good solution? In order to see that, we have to show that actually the solutions for the Duffing equation are always bounded for all times t. And let's do that in the next part of the video and see that, in fact, let's see that the solutions for the Duffing equation should actually remain bounded. And that is why this particular expansion and this resonant term, just as a reminder, actually this is the resonant term that we've been talking about, and that this is the fact that there is a resonant term that seems to give solutions which will blow up in large times is actually an artifact of the fact that we are only expanding this to first order and epsilon. But in order to get rid of that, we have to actually do an expansion which is an infinite order in epsilon, which is very, very hard. And so let's first see that the solutions will actually remain bounded in the next part of the video, and then we'll see how to sort of come up with a new method that will give us a solution which is a better approximation to the differential equation. So see you in the next part then.